segments, I've shown you how to find the area of a region caught between two curves over a span of values. Well, what if we took the area or the region in the plane and we actually revolved it around an axis of revolution? Well, if we did that, let's say for this example, I take this shape and I trace along it in the plane, and then I revolve that around the x-axis. And the notation that kind of designates what axis you're revolving it around is this little loop with an arrow. So here, if I revolve this shape around the x-axis, I actually get a 3D object. And I get a 3D object that's called a solid of revolution. Now, for this particular one, when I spun it around the x-axis and revolved it, I get this wedding decoration, which is a bell. But a key component of doing these problems and setting them up correctly is being able to visualize what kind of 3D object you're getting, and then using that information to set up the right situation in order to calculate the volume of that solid. Now, another shape that we could take is possibly this shape. So we're going to take and trace, we're going to trace along the curve and then revolve that around the x-axis. I would get a sphere. So we could even use what we're going to do in this process to find the volume of a sphere. Well, what is the process? There are a few that we'll talk about in later segments, but this one specifically is talking about something called the disk method. And the disk method, what we need to do is to back up a little bit and remember from geometry how to find the volume of a cylinder. Now, a cylinder is when you take a region in the plane and you pull it through space to the same region, and that creates a cylinder. And the volume of a cylinder is the area of the base shape times how far apart those base shapes are when you pull them through space. Now, if I say I have a right circular cylinder, that means the base is a circle and I'm pulling the circle through space directly over the other one. So it's sitting upright. The sides of the cylinder are perpendicular to the base. So for a right circular cylinder, my volume is the area of the base, pi r squared, because base is a circle, times h, the height you pull it through space. We're going to hold on to that for a minute and then think again about our solid of revolution. Our goal here is to find the volume of the solid of revolution. Well, when I have the region that we're interested in spinning around an axis of revolution is shaded along the axis of revolution, so it's tight against the axis of revolution throughout the entire interval. And for our discussion of this, even though our original shape wasn't a function, I'm going to cut it at this vertical line B here for our demonstration. Well, if I take little clips of that region and I do them vertically and I spin that around the x-axis, then we're going to have like a shape like this spun around the x-axis. I'm going to get little discs. Now, I had to make this a little bit thicker for demonstration's sake, but we take them infinitely thin so that it actually can be thought of as if I have a disc as we go. So kind of like a hockey puck. And then we just add up the volumes of all of these little discs throughout the interval. Now, the disk method specifically is when the region is against the axis of revolution through the interval. So shaded touches the axis of revolution through the interval. And the slices that you're taking are perpendicular to the axis of revolution. So I took these slices perpendicular to the axis of revolution. then I will have what's called the disk method. Now there's two different scenarios. One is if you take horizontal axis of revolution. So in this case, it's my x-axis, so that's horizontal. And if my axis of revolution is horizontal, and I'm taking my slices vertically, then my volume is pi times the definite integral from a to b of capital R of x squared. So capital R of x is the radius of your little slices that you're taking. And then dx is the differential dx because we have our subrectangles that are our slices that we're taking that we also revolve around the axis of revolution are vertical. So that is our equation for our volume using the disk method if my axis of revolution is horizontal. Now, if the axis of revolution is vertical, so let's say you had the y-axis for an example, and you were spinning it around the y-axis, so you have a vertical axis of revolution. If you take your slices perpendicular to that, you would have horizontal slices that would be spun around, so your discs would be going that way. Then I have to have my little differential dy. And so my volume will be pi times the definite integral from c to d of capital R of y squared dy. So a key component of this is also graphing the region of that you're going to spin around your axis of revolution, graphing and denoting what your axis of revolution is, and then seeing that it's tight against the axis of revolution if you're using the disk method, being able to set up your radius that you're going to square and go through that. So we're going to look at a couple examples. Our first example is to find the volume of the solid obtained by revolving y equal x squared plus 1, x equal 1, x equal 3, y equals 0 about the x-axis. So I've graphed our region here. Y equal x squared plus 1 is a parabola with a vertex of 0, 1. X equal 1 is a vertical line at x equal 1. X equal 3 is a vertical line at x equal 3. And then y equals 0 is the x-axis. So once we designated that region, and then about the x-axis, make sure you show that loop. And again, you did this right after finding the area of a region in a plane. So the area formulas don't have the pi or the square of the radius and that kind of thing in it because it's just the area of a plane. It's when we're revolving that region around an axis of revolution that you get this solid of revolution, and our slices are 3D objects, so we have to look at our volume of the 3D object. Okay, so looking at this, the region is shaded tight against the axis of revolution over the entire interval, and I'm going to take vertical subrectangle slices of that region that gets revolved. So that's dx, and my formula is pi r squared dx, and then over that interval. Well, my interval is from x equal 1 to x equal 3. My radius is from the x-axis up to the parabola. So that is just the function output of the parabola, which is your x squared plus 1. So here's my radius of capital R of x, x squared plus 1, but that radius has to be squared, and then dx. Now when we're going through and integrating it, we need to multiply out the binomial before we do the integral. So the volume is pi times the integral from 1 to 3 of multiplying out this binomial. I have x to the 4th plus 2x squared plus 1 dx. Integrating, I have volume is equal to pi on the outside, and the antiderivative of x to the fourth is 1/5 x to the fifth. The antiderivative of 2x squared is add 1 to the exponent, divide by that, 2/3 x to the third. And the antiderivative of 1 dx is x. And now that we've already integrated, we're not going to do the integral symbol anymore. We're going to show our vertical line to say we still need to put in the values to do the definite integral from 1 to 3. Now remember, you're going to plug in the 3 minus plug in the 1. So my volume is pi times 1/5 3 to the fifth plus 2/3 3 cubed plus 3 minus, and make sure you use your parentheses, put in the 1, 1/5 1 to the fifth plus 2/3 1 to the third plus 1. And when you go through and do the work for that, you'll get that the volume is pi over 1 times 1016 over 15, which is 1016 pi over 15 cubic units. Another example of using the disk method and looking at this where I have a horizontal axis of revolution and vertical subrectangles is find the volume of the solid obtained by revolving f of x equals the square root of sine x, g of x equals 0 on the interval from 0 to pi about the x-axis. So I've graphed f of x equals the square root of sine x here. It's on the span from 0 to pi. G of x equals 0. Remember, g of x is just another name for y. So that's y equals 0. And y equals 0 is the x-axis. And so shading this region is the region we're spinning around the x-axis. And I see the shading touches the axis of revolution throughout the interval. And I'm going to take vertical subrectangles when my axis of revolution was horizontal. So I'm going to use the disk method. So its volume is pi times the definite integral from 0 to pi. You want to add up all those volumes throughout that interval of the square root of sine x quantity squared. Remember, it's r of x squared. And my radius is going from the x-axis to the curve, and the output of the curve is your square root of sine x. Well, the square root of sine x squared is just sine x. So my volume is pi times the antiderivative of sine x, remember, is negative cosine x. And then I'm going to evaluate that from 0 to pi. Put in the pi minus put in the 0. And be really careful about your negative signs. A lot of times if you don't get these quite right, go back and check that you had your parentheses correct and that you've been careful with your negative signs. So I have pi on the outside from my disk formula times a quantity. The cosine of pi is negative 1. So the opposite of negative 1 is 1. Then I have minus a negative, so that's plus. And the cosine of 0 is 1. So it's pi times the quantity 1 plus 1. So that's pi times 2, which is a volume of 2 pi cubic units.